Hi guys. This is 8B, and I'm going through a couple of the example questions here. A lot of the theory comes in the first video, and this is just having a look at some of the questions. There are many questions that could be asked from what we've just gone through, and so we're obviously just looking at a couple. So let's look at the first one. There's example 2. They say use your GDC to find the values within this range between minus pi or minus 180 degrees all the way up to 2 pi radians or 360 degrees. You'll get this, yeah, right. So sine of x is equal to a half. Well, you're going to use your calculator on this one. Now, you can do sine to the minus 1, but when you undo sine, you'll get x is equal to sine to the minus 1, 0.5. And that will give you pi over 6, in fact. Pi over 6, or in fact, this answer here if you write it as a decimal. Now, for myself, I would use the sine graph to find, and the symmetries in my sine graph to find out where my other solutions are. I know that here is pi, I know that here is 1, I know that here is minus 1, and I've been asked for inverse sine essentially of 0.5. So I've got one solution there, pi over 6, and I've got another solution which is pi over 6 less than pi, which turns out to be 2.62. Now they say that this graph, see this one is going up to pi. Now if I take that back to pi, I will get to here. Okay, so there's my minus pi, taking it back there, taking back a length of pi. You can see that I've got no more solutions there equal to 0.5. So there's only two solutions, two x values, which give me out the height of 0.5 in this case, and so we found them here. It suggests that you use your GDC. It says you should always plot a graph in order to ensure this. If for those of you familiar with the shape of the graph and the symmetries within the graph, it will be sufficient to sketch the graph and use the symmetries within the graph. But obviously, if you're quick with your GDC, you can use your GDC to find this second value here as well. Some people might also know about the cast diagram. I don't want to go into this too much just at the moment, but the cast diagram, some people know about this. It's kind of, it matches up with the unit circle. I personally don't use this, but it says that between 0 and 90 degrees, all of your ratios are positive. And then after that, your sine ratio is positive, and then your, hang on one second, all here and your your sine is positive there and your cosine is positive there. So cast reads around this way, or some people call it acts reading backwards as well. Now, I don't use this very often. You can skip this if you want to, but if, for example, you know that sine is your height of 0.5, then there's your first triangle. First triangle has this angle of 0.524 in radians in the corner here. Well, we know that if we're going to have another triangle over here which has the height of 0.5, which is sine. So that angle there is what we're looking for, and that's going to be pi take away your 0.524. The same angle here is the same angle here. We've got some symmetries in this diagram. If you've done that before and you like that, you can use that, but they're suggesting that you use your GDC all the time here. Right, for the next one, it says cos is equal to minus 0.2. Again, you can draw out your cos diagram here, or you can use your GDC for that one. I'm not going to go into that now. Okay, and just looking at, let's look at, just switch off my pen. Let's look at the example 3. Example 3 comes from this exact triangle which they draw to the side, and I put a little video up about exact triangles. I wouldn't worry about them too much at the moment, but you can read through this question as well. You can see that they've come up with this example triangle over here. Now, what's important to note is that there are a few exact triangles which allow you to get out exact ratios. So there's this one, But there's also, you do a triangle which is 2 by 2 by 2, an equilateral triangle, and split that in two, and this now has the length of 1 at the bottom. If you use Pythagoras, you can see that this has the height of the square root of 3. This is 60 degrees, and this is 30 degrees here. Now, this triangle enables you to get out exact answers for things like, let's say, sine of 30 degrees. I've got 30 degrees at the top. The opposite to that would be the 1. The hypotenuse is 2. Sine of 30 is equal to a half. So you can get out exact values from this triangle here. It's a special triangle which helps you get out particular nice ratios, which turn up at 30 degrees, 45 degrees, 60 degrees, and also 0 and 90. 0 and 90. There's kind of a nonsense exact triangle as well, where you have a length of 1 there, a length of 1 there, a height of 0, and an angle of 0 there, and an angle of 90 degrees here as well. It's kind of a nonsense triangle because it's essentially a line. So these triangles here will enable you to get out your sine of theta, your cosine of theta, and your tan of theta for 0, 30, 45, 60, 90. This would be a nice table for you to make and to have in your books as a reference. Guys, the lesson's about to start actually, so I'm going to have to stop there. Thank you very much.